Hello friends, we are starting a new topic today. I will say this is one of the most important topics in your entire COA course. In today's video, we'll discuss about multiplication of binary numbers. I will say integer binary numbers. We'll discuss about two different cases. One is for unsigned binary number multiplications and second case is signed binary multiplications. So for signed binary multiplications, we'll discuss about Booth's algorithm in this video. Booth's algorithm is one of the most important algorithms in your entire COA course. So please watch this full video and do comment if you have any doubts or queries. If you like my video, please do subscribe the channel. Let's start the video. Before we move for the signed integer multiplication in binary, let's quickly revise the multiplication technique for unsigned binary numbers, which we have already seen in the last video. So how to do that? Suppose these are the two unsigned binary numbers I have. I am talking about integer numbers. Floating we have discussed in the last video. We have a separate video for that. Now suppose these are the two numbers I have. One is 11 and one is 13. 11 is 1011, 13 is 1101. So how to do this multiplication? Using traditional approach? Simple. Just like our decimal multiplication, what we will do? We will multiply all the digits from the first number with the first or rightmost digit of the second number. So 1011 into 1 is 1011, right? Then we'll just skip one bit from the right hand side and then we'll multiply all the digits from the first number with the second rightmost digit of the second number. So 0 into 1011 is 0000. This is how we multiply for our decimal multiplications, right? There is nothing new. And finally we'll just add all the bits like this and we'll get the correct result. Fine. For unsigned binary numbers, integers, if you follow this approach, you will get the exact values. It will work perfectly fine. Now, your computer won't understand like this, right? To make your computer understand about this multiplication technique, we have an algorithm for that. So this is not Booth's algorithm. This is the traditional way to multiply two unsigned integer numbers. So for that, we have a flowchart or algorithm. So what is that flowchart? We'll start. Then we have CA0. I will do better. I will take one example and I will explain this flowchart. It will be more easy for you. If I directly explain this flowchart, it may not be easy for you to understand, right? So better I will take one example. So I am taking one example and we will see how it works. Fine. What we have? We have this algorithm in front of us. We will exactly follow this algorithm. Please pay attention. What this algorithm says, we'll start the algorithm here. Okay, fine. Immediately we have an initialization box. In initialization box, what we have? CA equals to 0. Please pay attention. CA equals to 0. These are nothing but some registers where initially I am making it as zeros. What is this C register all about? This C register is all about to store the carry out bits, and this A bit will be initially 0. This A register is initially zeros. So how to fill it? C equals to 0. A, I am putting 4 zeros. Why I am taking 4 zeros? Because I am multiplying two numbers having 4 digits. Next I have M for multiplicand, Q for multiplier. So randomly I am taking multiplier as 11 and multiplicand as 13. Just convert it back to binary. 13 is 1101 and 11 is 1011. So both the numbers are having 4 bits. So exactly 4 bits I am taking in A also, and initially I am making it all zeros only. So I have C, A, Q, M is clear for you. That is what your initialization box says to take it. Now see, we have one more register called count. So count also you have to take. This count is nothing but number of bits you are considering to perform this multiplication. So for both the numbers I have 4 bits. So 4 will be there, and this is initial phase. So this box is done. Fine. Next what we will do? We will go for this conditional statement box. So what it says? I have to check whether my Q0 equals to 1 or not. What is my Q0? This is my Q. This is Q0, right? This is Q0, Q1, Q2 and Q3. This is A0, A1, A2, A3, M0, M1, M2 and M3. So I have to say Q0. So Q0 is what? 1 here. So the conditional statement says whether my Q0 is 1 or no. It is yes. So I will move this side, right hand side. If it is yes, what I will do? A equals to A plus M. I will perform A equals to A plus M, and if there is any carry out bit, I will store it in C. Fine, we'll do the same thing. So what is my A? 0, 0, 0, 0. What is my M? 1, 0, 1, 1. So if I do A equals to A plus M, 0, 0, 0, 0 plus 1, 0, 1, 1 will be nothing but 1, 0, 1, 1 only. So 1, 0, 1, 1, and there is no carry out bit. If you add these two, you won't get any carry out bit, right? So C is 0. New A is becoming 1, 0, 1, 1 because I have added these two. And Q is as it is whatever I have. M is also as it is whatever I have. Count also as it is whatever I have. So this box is also done. Then we'll come for this box. So here what I have to do, shift right CAQ. I have to perform right shifting starting from C ended with Q. Fine, what is my C here? What is my Q here? So I have to shift all these bits right hand side, one bit to the right hand side. So if I do so, how it will look like? See, this 0 will come here. I am shifting one bit right hand side. This 1 will come here. This 0 will come here. This 1 will come here. This 1 will come here. This 0 will come here. You understood that, right? See the direction? 0 is coming here. 1 is coming here. 0 is coming here. 1 is coming here. This 1 is here. This 1 is here. This 1 is here. This 0 is here. This 1 I don't have any place to store because I can store only 4 bits, right? So you can eliminate this one. You understood that? Now this place is empty initially because this 0 I have shifted to right hand side. Now you can just put one 0 to fill it, nothing else. I cannot make it empty, so I am putting it one additional 0. Fine. So after that what I have to do? After shifting I have one more statement, one more line here. Count equals to count minus 1. What was my previous count? 4. So I am making it as 3. Fine. So this part is done, and then I will check whether my count equals to 0 or not. What is my count now? 3. After deducting or after decrementing by 1, it's 3. It's not 0. If it is not 0, then I will come back to this side once again. So this is first phase or initial. This is the first phase we have done with. Understood that? Now again I will check here. What is my Q naught? What is my current Q naught? After shifting, what is my current Q naught? It is 1. Sorry. The current Q naught is 0. Right? We are here. The current Q naught is 0. If it is 0, then what we will do? See, whether my Q naught is 1 or not. No, it's not 1. So if it is not 1, I will directly shift the CAQ. I won't perform any arithmetic or anything in between. If it is yes, then only I will do arithmetic, right? So what I have to do? I have to shift only. So you start shifting. What was C? C will come here. So 0, 0, 1, 0. This 1, this 1, this 1, this 1. What about this 0? I don't have any place to store, so you can ignore it. And this place was empty because this 0 is shifted here. So you have to fill it with 1, 0. And then count equals to count minus 1. So count is 2 now. From 3 it's becoming 2. And my second phase is done. Again I will say whether my count is 0. No, it's 2. So again I will come back here. Now tell me what is my Q naught here. This is the Q naught, updated Q naught, which is 1. If it is 1, then I will come this side. What I will do? A equals to A plus M. What is my A? 0, 0, 1, 0. What is my M? 1, 0, 1, 1. Just add it. 0, 1 is 1, 1, 1 is 0. Carry out bit is 1. So 1, 0 is 1, 0, 1 is 1. Carry out bit is 0. Fine. And rest all the things are same. Q, whatever we had from the previous step. 1, 1, 1, 1. M is 1, 0, 1, 1. Count is 2. So after this, what I will do? After performing this arithmetic, we'll go for right shifting CAQ. Do it. This 0 will come here, this 1 will be here, this 1 is here, this 0 is here, this 1 is here, 1 is here, 1 is here, this 1 is here. You eliminate this one. So this empty place I am filling with 1, 0. And finally, I have M as it is 1, 0, 1, 1, and count equals to count minus 1 is 1, 1. So third phase is done. So still my my count is not 0. So what I will do? I will again repeat the same steps. So what I have here, Q naught equals to 1 or not. Check it. What is my Q naught? Yeah, it's 1. If it is 1, again I will come this side. I have to perform A equals to A plus M. What is my A? This one, 0, 1, 1, 0. What is my M? 1, 0, 1, 1. Just add it. 0, 1 is 1, 1, 1 is 0, 0, 0. And I have a carry out bit 1 here. Check it. 0, 1 is 1, 1, 1 is 0. I have a carry out bit. 1, 1 is 0. I have a carry out bit. 1, 1 is 0. I have a carry out bit. So I am storing it here. Then whatever Q I have, whatever M I have, whatever count I have written as it is. Understood that? Next, just shift it right. So this one is coming here, 0 is here, 0 is here, 0 is here, this one is here, 1 is here, 1 is here, 1 is here, this one you are implementing, and this empty place I am getting with 0. Whatever M you had, you just put it as it is, and now count equals to count minus 1 is becoming 0. So my count is 0, yes, this is the end, so I will go for the end. So once I have ended the algorithm, what is the final result? The product is in AQ. So A and Q together will be the result. What is my A? 1,000,000, and what is Q? 4 times 1. So this is the final result, 10001111. If you convert it back to decimal, you will get 143, which is exactly correct. 13 into 11 is 143. So this is how the multiplication of unsigned integer can be performed using this algorithm. And your computer follow this algorithm to perform any unsigned multiplication for any binary numbers. So I hope this is clear. Now the problem is the same approach we cannot use for signed numbers. If you practice signed numbers and if you follow the same approach whatever you have done for unsigned numbers, sometimes you may get correct result, but not always. Most of the times you will get incorrect result only. So for that, what is the solution? For that, we have a separate algorithm, which is Booth's algorithm. And this is one of the most important topics in your entire COA. I told you. Most of the times you will get at least one question from Booth's algorithm if you are going to appear for your end sem exam, mid sem exam, or any other competitive exams. Fine. Now this is how your Booth's algorithm looks like. This also I will explain with the help of one example so that it's easy for you. Instead of simply discussing this algorithm, I will take some example and I will explain how it works. So I am taking one example here. Say I have a multiplier 7 and multiplicand -3. I can multiply now signed number also, right? We are using Booth's algorithm. This is not limited to unsigned. We can use signed number also. So 7 into -3 will do. Remember, in multiplication, this Q and M, you can alter it also. It does not matter which one is Q and which one is M. I can take -3 into 7 also, right? A into B or B into A will always give you the same result. So there is no issue with multiplier and multiplicand. So don't worry if you are mismatching your multiplier and multiplicand in the exam. It will give you the same result. So I have Q equals to 7. This is 7. This is -3. So I have converted back to binary. And in Booth's algorithm, one more thing I need is -m. Whatever multiplicand you have taken, whatever it is, 1 1 0 1, whatever you are getting, this is m. I need -m also. So somewhere you note it -m in the answer script or wherever. You just note it -m. We need it in future. Fine. Now we'll start the algorithm. What we have? Start. Then a equals to 0. A equals to 0 is fine. I am putting all 4 zeros because I am taking 4 bits. Then you see one more register I have here, Q -1, which was not there in the previous case. Q -1, which is initially 0. So Q -1 is 0. I am putting here, and then M is equals to multiplicand. So multiplicand I am putting, multiplier I am putting here, count equals to 4 I am putting here. So initial phase is done, and I don't think there is any issue with this initialization box. So immediately after that I will come back to this conditional statement. Now in the previous case, what we have seen whether my Q naught equals to 1 or not. Only one condition was there, right? But here what we will say, Q naught and Q -1 together. This Q -1 is always 0 by default for the first or initial phase. Later on it will be keep changing, we'll see how. So I have to check Q naught and Q -1 together. So what is my Q naught here? This is the Q naught, right? Which is 1, and Q -1 is 0. So I will check these 2 bits, 1 0. What I have here? 1 0. So I have all the possibilities, these 2 bits. It can be 0 0, 1 1, 1 0 or 0 1. Based on the value, we will take the direction. What we have? 1 0. For 1 0, which direction I will take? This direction, left hand side. And what I will perform? A equals to A -m. That's why I told you to note -m somewhere. I need A -m also. So A equals to A -m. What is my A? 0 0 0 0. What is my -m? 0 0 1 1. Just add it. Fine. -m I already have, so A and -m you add it, it's nothing but A equals to A -m. So what are you getting? 0 1 is 1, 0 0 1 1 you are getting. Remember, in Booth's algorithm we don't have any space for carry out bit, so always you have to ignore the carry out bit. Fine. So 0 0 1 1 I got from here, and rest all the things you keep it as it is. Q whatever you have, q minus 1 whatever you have, m whatever you have, 4 whatever you have, you keep it as it is. So this part is done. After that I will come back to this box. What is this box all about? Arithmetic shift right. We'll do the right shift again. Where a q q minus 1. In the previous case whatever we have done, we have started from c, ended with q, right? C a q we have done. So here we will start from a, we will end with q minus 1. Do it. So how it will look like? This 0 will be here, this 0 will be here, this 1 will be here, this 1 will be here, this 0 will be here, this 1 will be here, this 1 will be here, and this 1 will be coming here. Fine, this one will be coming here. So I forgot to put this direction, but this one is coming here. Previously the last bit of q was eliminated because there was no space, but here I have. But this 0 I cannot store anywhere, you can just eliminate it. We don't have any space for that. I hope you understood that. Then rest m and m you put as it is, whatever you have, 1 1 0 1. Then count also I have to decrement by 1, count equals to count minus 1 is becoming 3 here. Fine. Now here you have to note one point. What to do with this empty space in A? Because this bit is shifted to right hand side, right? Now nothing is there here. Now what to put? In the previous algorithm or for unsigned multiplication, what we have done, every time we filled with 1 0, right? Wherever we got some empty space in C, we always put 0. But remember, in Booth's algorithm, you have to be very careful. This place is always not 0. You cannot put always 0 in this place. It depends on other bits of this A. Means it depends on the next 3 bits. It depends on this bit, this particular bit. Means if you eliminate this, you have 0 0 1, right? So you have to check whether this number is positive or negative, or what is the first bit, what is the MSB you have. If the MSB is 0, then you have to put 0. If the MSB is 1 here, you have to put 1. It's not always 0, fine. So here I have 0, so I am putting 0 here. So I hope it's clear. And rest of the things I have already explained. It's 3 now. Now my count is not 0. It will come back here and it will check again q naught and q minus 1. So what is my q naught and q minus 1 now? What is the q naught I have? 1. What is the q minus 1 I have? 1. So if it is 1 1, I will directly come here, because this path is only for 1 1 and 0 0. And here I don't have any arithmetic operation. Simply I will do shifting a q and q minus 1. Do it. So if you do so, this 0 will come here, this 0 is here, this 0 is here, this 1 is here, 1 is here, 0 is here, 1 is here, this 1 is here. Fine. Now what to put here? I know this is starting with 0, so I am putting 0 here. And this m is same, 1 1 0 1, and count equals to count minus 1, which is 2. So second phase is done. My count is not 0 yet. What I will do? Again I will come back here and I will check for q naught, q minus 1. Check it what I have. Now this is the updated one. So what I have? Q naught is 1, q minus 1 is 1. Again I got 1 1. If it is 1 1, again I will do the same operation here. No arithmetic because of 1 1. So what I will do? Again I will do right shift. Do it. This 0 is here, this 0 is here, this 0 is here, this 0 is here, this 1 is here, 1 is here, 0 is here, 1 is here. Fine. M is whatever you have as it is, and count equals to count minus 1 I am doing. And this bit again I am putting 0 because this MSB of the rest 3 bits are 0, so it's 0. Fine. But my count is not 1 yet, so I will go for the next iteration again. In the next run, what I will check? Q naught, q minus 1. Check it. What is my q naught and q minus 1? It's 0 1 now. So for 0 1, I will take this right path. What I have? A equals to a plus m. Now I have to do a equals to a plus m. So what is my a here? 0 0 0 0. What is my m here? 1 1 0 1. Just add it. 0 1 is 1, 0 0 is 0, 0 1 is 1, 0 1 is 1. Fine. After adding, what I have to do? This all the things you put as it is, whatever you have. 0 1 1 0. Here I have 1. Here I have 1 1 0 1. Here I have 1. Then come back to this box and do the right shifting. Fine. So this one will be coming here, this one is here, this 0 is here, this 1 is here, this 0 is here, 1 is here, 1 is here, 0 is here. Now check it, what to put in this blank space here. You cannot put 0 now. Why? Because the MSB of rest 3 bits are 1. So you have to put 1 here. Fine. 1 1 1 0, 1 0 1 1 0, 1 1 0 1, and this is count equals to count minus is 0 now. So my flowchart or algorithm is ended here because I don't have any more iteration. If it is ended, what is the result? The result is AQ, just like your unsigned. Here also the final result is stored in AQ. What is my final A? 1110. What is my Q? 1011. So 11101011. If you convert it back to decimal, you will get minus 21. Now how to convert it back from 2's complement to decimal, I have already discussed in my second video number 2. You can go back and check it how to convert it back. So this is how Booth's algorithm works. I think